Hi! For today's video, we will do a basic electrical engineering activity which highlights the Kirchhoff's law. To do that, we will utilize Ohm's law and second, the Kirchhoff's law. And our objectives for today is to first, verify the Kirchhoff voltage law, second, to verify the Kirchhoff's current law, third is to gain experience for our multi-tester, which is combination of voltmeter and ammeter, and lastly, which is our fourth objective, is to construct a circuit based on the schematic diagram. Woo! The Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points.
To apply the Ohm's law in our circuit, if we have 20 volts in this particular circuit and 10 volts when it passes through a resistor, it means that the current in this point would be higher compared to this point, since the current is directly proportional to the voltage. Since the voltage lowers at this point, then the current will also be lower.
So the Kirchhoff voltage law states that for a closed loop series path, the algebraic sum of all the voltage around any closed loop in a circuit is equal to 0.
If we apply the Kirchhoff's voltage law, we will have two loops. This would be the first loop and this would be the second loop. And as what it states, the voltage of these any closed loop series path would be equals to 0. So if we have a voltage of negative 10 here and a voltage of negative 9 here, and if we add that one, it would result to negative 19, and our source here would be positive 19, so 19 minus 19 would be 0. The same at this point. If we have negative 5 here and approximately negative 5 here, if we add this one, we will have negative 10. And since it has already a resistor, our source here would be 10 volts. So 10 minus 10, we will have 0.
Kirchhoff's current law states that the algebraic sum of all currents entering and exiting a node must equal to 0.
To apply the Kirchhoff's current law in here, in this first loop, if we have this as an input and this will travel to an output, and we have here a 0.012 ampere of current, it means there would be also 0.012 ampere detected in the multi-tester, since KCL states that whatever the input of the current would be equal to the output. At this point, we are measuring the correct resistance and voltage that are included in the circuit using the multimeter. If you're wondering why isn't it very accurate compared to theoretical measurements, it is because of the tolerance and the resistors.
How did we get our theoretical values of voltages across each resistor? So the very first thing that we did is we treated this one whole circuit as a circuit with two main loops. So as you can see, this is the first loop, which is composed of resistor 1 and resistor 2 that are in series. And this is the second loop, which is composed of resistor 3 and resistor 4, which is still in series. Now these are the main informations that we hold in getting or in calculating the voltages across each resistor. We started in getting the voltages of each resistor in loop 1. So here, in loop 1, we have the given voltage is equal to 20 volts. We then get I, or the current, using Ohm's law, where R is equal to 1680 ohms, which we get from adding the resistance of resistor 1 and resistor 2. Now we substitute this to our formula, I is equal to V over R. We do the math and we get 0.012 ampere. Now, since we have already the value for the current, we then solve for the voltage in resistor 1 and resistor 2. So we substitute this to our formula and we do the math. As you can see, in resistor 1, the voltage is 12 volts, and for resistor 2, the voltage is 8.16 volts. Next is we moved on to our loop number 2. where we start taking the voltages for each resistors. So for loop 2, the given voltage is 10 volts. We still get I using Ohm's law, where here in this case R is equals to 940 ohms. It was took in adding the resistances of resistor 3 and resistor 4. Now we substitute this to our formula, I is equals to V over R, and get 0.011 ampere. We substitute this to our formula and getting the voltages for R3 and R4. As you can see here, we substituted the datas and do the math. In resistor 3, the voltages across resistor 3 is 5.17 volts, and for resistor 4, it also has 5.17 volts. Now we verify Kirchhoff's voltage law on both loops. Here, in our loop number 1, we use this equation, Vt, or the total voltage, plus negative V sub R1 plus negative V sub R2. We substituted our formula. We added negative 12V plus negative 8.16V, that is negative 20.16, or approximately 20. So we have 20 volts minus 20 volts. We have an answer of 0. For loop number 2, same case, same steps. We substituted our data. We added negative 5.17 volts plus negative 5.17 volts. That is approximately 10. And we subtracted it from the total voltage of 10 volts and still get 0. So as you can see, in both loops, we arrived on the same answer of 0, which thus we can say that Kirchhoff's law holds true as the individual voltage drops across these closed loops, respectively on loop 1 and loop 2, adds up to the total voltage, which is 20 volts and 10 volts respectively.
At this point, we will measure the voltage across resistor 1. The multimeter is connected in each side of the resistor in order to detect the voltage that passes through the resistor. Same goes to the other resistor, where we place the resistor in between the test probe to measure its voltage. We did the negative to positive measurement in order to get a negative value of the voltage. So when we get the summation of all the voltage in one loop, we will get a 0.
So now we are going to solve for the current. So we are going to use the current formula, which is current equals volts of the specific resistor over the resistance of the resistor. So from our measured values, we obtain 12 volts. So we just divide it with the resistance, which is 1000 ohms. The value we obtained is 0.012 amperes. Next is for the second resistor. Our volts we obtain is 8.16. We divide it by the ohms, which is 680. We would obtain 0.012 amperes. Next, for our resistor 3, we obtained 5.17 volts. So we divide it by the resistance, which is 470. We would obtain 0.011 amperes. And next is the resistance 4, which has the similar value. We have 5.17 volts over 470 ohms. We have 0.11 amperes. Here is our diagram, practical circuit with the values.
At this time, we measure the current across the resistors. The multimeter is still connected in each side of the resistor to detect the flow of the current that passes through it. If we observe clearly, the current is just 0.01, which we can assume that the electricity weren't gained or lost. In other words, there is a conservation of electricity at this point.